Okay, so what I want to do, and I hope I can do this fairly quickly and just kind of go through this in the video. If you can't keep up with me here in the room, that's okay. You can look at it later. You can kind of see the idea of what I'm doing, and we can discuss it. Anyway, if you have questions or if you have want to talk about different ways of doing specific things, definitely raise your hand. But I'm hoping this video doesn't have to become insanely long. So these are the exercises that we're starting with here, and I just start with this code base here, unchanged. So I'm going to try to go through this in this order, but I'm more or less just going to kind of go through this code. The first thing that it's nice to look at is the Vertex Shader, which basically takes our vertices, takes our points, and applies any geometrical transformations that are needed to it, and finds, in the end, its place kind of in the world relative to the camera after having done the projection. So the first thing we do is we want to add the normal as well. Since we're working in 3 dimensions now, then the position alone is not enough. So I'm going to add another attribute here, and I'm going to call it a normal. So now I've added the attribute. In the shader, I want to do something very similar to that here. The only reason I'm doing this is basically since we're sending in 3 values at a time for the vertices, that is 3 for the position and 3 for the normals, but I'd like to do the 4x4 matrix multiplications in the shader. I'm just adding 1 at the end of the position and 0 at the end of the normal. So now this is a vector rather than a point. This normal here, oops, make sure that this is called normal. So the normal takes the attribute normal, makes it into a homogeneous coordinates for the normal, and it's used here in these calculations. But in order for these calculations to work kind of globally, we have to make sure that we take it out of the local coordinate system, or local coordinate frame that it's sent in, and multiply it with the model matrix, just like we do with the position. So at this point, we're working in global coordinates. Right now, we're not really using the position at all, but in the end, the position and position of lights and all kinds of things will be used doing proper lighting calculations in this part of the code. But for now, you can just imagine lighting calculations as being something hard-coded. You just have to make sure the normal is in global coordinates, and then this will just work. However, we can't really change the lights. We can't change the color of them. We can't change the position of them. We can't move them around, change the direction of them. All right, so I've added the normal to the shader itself, which is the simple 3D.vertex shader. Now I'm going to go into this class shader 3D, and what this class does is basically it's our communication device with the actual shader. So it sets up the shader, and it makes these handles like position location, model matrix location, so on and so forth. Makes these handles that we use to send values into the variables of the shader. In this case, we want to make a new variable here, a new handle called normal location, and we're going to say this is our handle to the shader variable a_normal. And then we are going to say that we are going to use this as an attribute. And what that means is the attributes are listed in the vertex lists. So when we call draw arrays, OpenGL will take the values from this list, send them to the vertex shader. When one has gone through the vertex shader, it'll take the next and send it on and so forth. It'll take them, in this case 3 by 3, the position values, and 3 by 3 the normal values, and send them onwards through the OpenGL pipeline. The difference between these that are used as attributes and the ones that are uniform variables is that the uniform variables we simply change, and after we change them, they remain the same until we change them again. The attributes are something that kind of flows out of these lists through the Vertex Shader, and the attributes kind of run the Vertex Shader. We run the Vertex Shader with these attribute values. The uniform variables we just set as we need each time. All right, so I've added a handle for the normal, and that's really all that's needed for now, except we may want to make sure that in this operation where we call vertex attribute pointer, which is basically telling OpenGL this particular handle here, in this case position location, which is the handle to the variable a position in the shader, it should be read from, the values for this variable should be read from this particular array. And then we're saying, okay, what is the type of the things that are in there? How many should be read together? This is, should we kind of skip some? Should we take 3 by 3 but then skip 3 of them? Stuff like that. For now, we just need to know we're reading 3 and 3 values together. These are floating point values. They're read into this variable, or the variable that this handle sets in the shader, and this is the array that we want them to be read from. So I'm going to make another one here that is called setNormal attribute. I'm going to use my handle normal location. Other than that, I'm just sending some vertex array into here. It doesn't matter what array that is. We'll look at that in the place where we actually send it in. So, saving this, we've done the changes that we need in the shader. Next, I'm going to go into the base 3D objects where I have this object cube. And what this object is it's basically these two huge lists of vertices that are just hard-coded in this case. And then it has this function draw. And what that does is it simply says, I am going to set a specific attribute here and say, these vertex lists that I have here are the lists I want to be read into the position variable and into the normal variable. So I'm going to add that here. I had position, now I have normal here as well. So the normals and the positions will be read from these arrays. Here, however, we simply say, I want you to start, this 0 means I want you to start at the first vertex in the arrays that have been set to be read from. So here we just set these arrays to be the arrays that are read from, that we read from, or OpenGL reads from, and then we say, from those arrays, start at the beginning and read the next 4 vertices from there. And I want to draw, it's called triangle fan. You can experiment with these things. What I want to add here, or we can actually, at this point, I believe we should be able to run this. So we just go into the program, see what happens if we run it. Just to see that something is happening. We have something there. Okay, so we have that one side from our cube. What we want to do, however, is we want to take the rest of these vertex lists and draw them as well, so we get a full cube. So you can see that 0 means start at the beginning, 4 means 4 vertices, but since they're read 3 and 3 together, as we can see here in shaders, we're reading them 3 and 3 values together. One vertex in this case means 3 values sent in. So the indices that we're using here are indices into OpenGL's vertex list that it has built from our floating point array. So when we say 4 here, I say I want to start at vertex number 4. That means kind of floating point number 12, since it's vertex 1, 2, 3, or 0, 1, 2, 3, then number 4 would be here. And then I'm going to read 4 from there. And then next I'm going to start at number 8 and read 4 from there. Start at number 12, read 4 from there. So and for every vertex here, there is a normal here. And the reason there are so many, even though there are only 8 corners on a cube, is because in this case we kind of need pairs of normals to positions. It's not enough just to have the 8 positions. We need to make sure that each position has its corresponding normal in the correct place. So we end up with 36 values for those 8 corners, because we need to make sure we have all permutations of the correct corners and their representative normals. All right, fair enough. So start at number 4 in draw 4, start at number 8, start at number 12, start at number 16, start at number 20. And let's see what happens if we go in here and just like this, Python, control 3D program. All right, so we actually have a 3-dimensional cube here. Yay, our first 3D program. So this is kind of what we need to do just to get this running. Now there's one fix that I want to look at here. I want to go into shaders. This fix, however, can be applied. Okay, I've already applied this fix here. In some cases, originally it just said simple 3D.vert. What I've added here is system path 0, which means the folder in which the file that's running now is, the folder from which we're running, rather than the folder which is open in Visual Studio Code. So if I skip this and just have simple 3D vert, it's a relative path from the folder that Visual Studio Code is open in. So this might be a subfolder of that, and then we're running it from the wrong place. It's nice to add this, so import system, and then add system path 0 plus this slash here. You can do this using path join or whatever else instead, but at least here we have a way to make sure that it's always running, or it's always doing the relative path from the from our main script. All right, so let's see what. So we've fixed this. We've made sure we see something. Yes. Cube. Added this, and we should have a black background with a single cube. Okay, now we want to look at the shader a little bit more. So we're going to go back to the shader, and I am going to add a uniform variable. So we have 2 uniform variables here. I'm going to add one more. What a uniform variable is simply a variable that we can change the values of anytime we want. We can't do it while we're drawing, but we can do it before we draw anything, after we draw anything. In this case, I'm going to make one for color. So uniform, sorry, this needs to be vec4. Vec4 means obviously just a 4-dimensional vector. Mat4 means a 4x4 matrix. We just have uniform, thank you, semicolon. It's nice actually to see if I skip this semicolon, what happens. I go in here, I run this, the program crashes, probably points to somewhere in, well, not my code, in some weird code. It's hard to find this. What is nice to check out first if you get an error like this that kind of doesn't really tell us that much, is to go up here and find this place here. So it couldn't compile the Vertex Shader. So there was an error in my C code for the Vertex Shader, or in my GLSL code. The shader compilation log here says something, okay, version directive missing warning, there's an error. Varying syntax error, syntax, okay. So it's line 9 here that it's telling me the error is in, but obviously it's because, you know, it was missing a semicolon here, so it tried to read onwards. You can get other errors here, but it's nice to check and see if you can read something from the shader compilation log. Shader compilation log is basically output in here with the function gl get shader info log with the ID for the fragment shader or vertex shader. All right, so we add this color variable here, and now we want to use it somehow. So I'm simply going to take this pure white color here, and I'm going to change that to the variable uColor. And then we need to send something in there. We need to send a vector that isn't just 1, 1, 1, 1. Instead, we're going to send some other color. So I've added a uniform variable. I've also added it to my code so that I use it somewhere. Now again, I need to go into my shader class and say, okay, I'm going to make a handle for this. I'm going to make a handle. I'm going to call it color location. It is going to equal, same as here, get a uniform location, and for the variable uColor. And this rendering program ID is simply the ID of the program, the shader program that I'm running now. So up here we built each of the shaders, the vertex shader and the fragment shader. We linked them together, and providing that that all worked and they kind of speak correctly together, we got a compiled rendering program. And we get a rendering program ID here. We link the program, connecting it to that program ID, and then we can use that program ID to set the variables for our shader. So uColor should have a handle now through color location, and now I'm going to go ahead and make a similar function here. I'm going to call it set solid color. Let's just say we send in individual variables for red, green, and blue. Now I'm going to use a different uniform function here, where I'm not sending an array in. Instead, I'm going to use the one called matrix, well, not matrix, uniform. Let's just see what we get. Uniform, we're going to send in 4 values, and let's say they're floating point values. So we're going to use GL uniform 4F. And into that, we are going to send, well, we're going to start with saying the variable that we're going to set is our variable color location. Color location. Then we're going to send red, green, blue, and I'm going to send 1.0 in the end because we're taking in a color as a 4-dimensional vector, but we're only taking 3 values here. I'm just going to set the alpha value to 1 all the time now until we start thinking about blending and transparency and things like that. So now we should be able to set a color into that. Now let's see if we can actually make that work. I'm going to go into my main program here. I'm going to go into my display function, and before I draw this cube here, somewhere before I start kind of doing the things with a matrix, I am going to say self shader set solid color, and I'm just going to send some values in here. Let's just make it purple. And see if this actually had an effect, or if it crashes. So now we have a purple cube. What we changed was in a lot of places. We needed to add the color to our lighting calculations in the shader. We needed to set up a variable, a uniform variable, for that change in the lighting calculations in the shader itself. Then we needed in our shader class, or basically anywhere in our program, to get a handle for that particular variable so that we could later send values into that using that handle. We had to set all of this, kind of this whole chain up, so that in a display function we can call the function that sets the values using that handle. That gets sent to the shader, so the next time the shader is run, it has a different set of values for the uColor variable. if I were to change this here to just some other value, let's not make it pure white, let's make it yellow. Then I'm simply setting other values to this. And I can change this at any point. I can change this and draw one cube, then I can move my model matrix to somewhere else, change the color again and draw a different cube, so on and so forth. So where are we in the exercise? Set solid color. Okay, now we want to look at the matrices a little bit. So we are using something called set model matrix. We have the model matrix here. In our shader itself, we have a model matrix variable. In the shader code here, we have a handle for the model matrix. We have another handle for what's called here the projection view matrix, which is just a way to send in one hard-coded combined matrix for the rest of the calculations, so we can ignore them for now. So we've got this handle. We also have a class for the model matrix, which builds a matrix, which is just a 16-value array of floating point numbers, but we can imagine it being a 4x4 matrix. So this 4x4 matrix here, we have a way to just fetch that. And in our main program here, before we draw this, we talk to the shader and say, okay, you have a function called set model matrix, and I'm going to send the matrix object, this array, from the model matrix class into that. In the shaders, what this simply does is it takes this array, it calls again GL uniform, which is simply saying, GL, I have values for you, I want you to put them into a variable. The variable I have a handle for here, model matrix location. That'll be the variable U model matrix in the shader. So I want you to put these values in, the values that you find in this array. This true here is telling us that this array is row major rather than column major. It just depends on, are the first four numbers the first row, next four numbers after that the next row, so on and so forth, or are the first four numbers the first column, next four numbers the next column, so on and so forth. So I decided it would look better in code, for instance here in matrices, if we can write the matrix like this in a single array and see the matrix looking like a 4x4 matrix like we're used to. If we would have this a column major matrix, then we'd kind of have to set the values differently or not see it as clearly. So it's just for us to make our code look better. I have decided that in my main code, I'm going to use, where are we? Shaders here. Make it be row major. Don't worry about that. Just continue using the code as it is, and it shouldn't be a problem. In the shader itself, we have U underscore model matrix and U underscore projection matrix, both of these being matrices. Here we simply multiply the model matrix with the position going into global coordinates. So here we're in global coordinates, global coordinates. Before we are in local coordinates. Here in the end, we multiply the position with the projection view matrix, basically a calculation adding both the view and the projection, and then we say GL position equals this. GL position is basically the output value of the vertex shader, which needs to be set in such a way that OpenGL can understand it throughout the rest of its calculations. So all of this is set up for the model matrix. So the only thing we need to do is we need to kind of add ways of doing something with the model matrix. So let's start by adding a translation. So this add nothing is just kind of a template. It makes an identity matrix, it adds that transformation, and obviously, that transformation does exactly nothing. But let's add something more interesting. Let's add a function here called add translation. So how's that going to look? I can change some values here, or to begin with, what do I want to take in here? What do I want my okay, X, Y, and Z. Fine. X, Y, Z. And where I'm going to put those, basically here, X, Y, Z. So now I've made a translation matrix here. I add the transformation, and you just have to trust me that this add transformation function works. It's basically doing a matrix multiplication through loops. So if we at this point make sure we have everything saved, make sure everything runs. It's always a nice thing to do once you've changed some code, just to see if your program runs the same as it did before. All right, now I want to go into my main program here, and instead of doing add nothing, I want to go ahead and say I'm going to add translation. And I want to translate it by 3 to the right. Let's just say that's all for now, and just see what that gives us. Okay, so it's further to the right. It has an immense perspective distortion here, but that's okay. We'll work on the lens later. All right, so it moved to the side. What I'm more interested in doing here is to draw more than one cube. I'm going to say this one was moved to the. I use push matrix to set the matrix. You can just study that yourselves. Push matrix and pop matrix are in here in matrices or in the model matrix class. We can talk about later. You can kind of study ways that you might be able to optimize that a little bit so that you're not always leaving the matrices that you push and pop for the garbage collection to pick up, but try to kind of reuse values and do that. The garbage collection is super nice in Python, but in computer graphics we're often working with vertices and stuff like hundreds of thousands of them within one frame, and if we're just always dropping our values after we draw each thing, there are pretty big amounts of things that the garbage collection has to do, and this can actually slow down our frame rate in our game. There's another optimization I'm going to look at here as well. All right, so where was I at? You can look at push matrix and pop matrix and that, but what it basically does, push matrix, is it copies the current matrix and puts it on a stack for push. So I'm saving my current state. Then I do some stuff to it. Then I do pop. Then I simply get the top value, the top matrix from the stack, and overwrite my current matrix with it. This leaving the original matrix for the garbage collection to pick up. So if you could do something about this, like copy the values without leaving anything, without dropping anything, even making a stack that has kind of just 10 values in the beginning and you never actually throw them out, you just change their values. In some cases that might make your program better optimized. You just have to decide which is quicker or which drops my frame rate less, me copying more values or the garbage collection having stuff left for it to pick up. In many cases, copying a little bit more values and doing a little bit more checks in your own code can be faster than just dropping things from the garbage collection. Anyhow, let's go back to the main program. I am going to draw another cube here. I'm going to transform that one, translate that one 3 up. Let's draw one more. Transform that one 3 closer to us. I think that's -3. Let's also set a different color for each of them. So let's make another purple one here. And let's just have a blue one as well. Okay, so we have 3 cubes here. Each of them pushes the matrix, adds a transformation, pops the matrix. It might be better optimized in some cases to add this translation, then not pop the matrix, but just add another translation that both negates this translation and adds another. If you're drawing like a structure that's hanging together, like drawing a full maze, and the maze understands how the walls are interconnected, sometimes doing these kinds of incremental transformations or incremental translations is better than constantly pushing and popping for every single cell. You just think about what might be best optimized. Let's see what happens if we run this. Okay, so we have 3 different cubes in 3 different places in 3 different colors. Great. What's actually happening in our code here, if we go into the actual Vertex Shader, is that when we send in the values for the cube the first time, then there's a certain value for the model matrix, and that model matrix affects the actual position that is used to calculate the light and thus the color, and it affects the final position where everything ends up, because the model matrix is different in each time. The next time this runs through, the model matrix will be different, the positions in global coordinates will be different, the colors and lighting and everything will be different because the model matrix affected the normal as well. And thus we get, even though the color, also that's an interesting thing to see, even though the color is always the same, if you just look at one of these cubes, this has 3 different blue colors, this blue, and this blue. Because the lighting calculations and the normals and the positions, everything is affecting this. Not only the color variable, but also the normal, the model matrix, its location in global coordinates, so on and so forth. Everything affects the final color for a pixel. So this pixel here is in a much darker blue color than this pixel here, even though they're both defined with the same variable values for the variable U color. So okay, should we go through the scale and rotate as well, or do you feel that's something? All right, cool. So matrices, let's just quickly add that. So we had add translation there, add scale. What's that going to look like? Okay, another XYZ, we can say SX, scale Y, scale Z, and we're going to put them here, right? SX, SY, and let's make this line up as well, SZ, and then we simply add it to our matrix. So now we should have working scale, working scaling. So we go into our main program, and I'm going to take, let's just look at what it looks like to begin with. So we can kind of remember what this looks like. Okay, let's take the one that's here to the side, the yellow one, and make it bigger, and let's take the one furthest away and make it smaller. So add translation. This is the yellow one. Let's add a scale. Okay, before we do the other ones, let's just focus on one at a time, just so we can see the changes. So yeah, let's make it 3 times as big in each dimension. So we're actually making it 27 times as big. Now we can look at this. So yes, the yellow cube is bigger. What if we add the scale before we add the translation? What happens then? What do you expect to see now if I run this program? Same thing? Someone else? Yeah, I expect to not see the yellow cube this time around. Well, I see a little corner of it. So we have a super wide lens, so it caught it. But it translated 3 times as far as well. So it translated kind of 9 in global coordinates because we first scaled, then we scaled the coordinate frame that the model matrix is affecting from then on. So when we added the translation, we're translating within that scaled coordinate frame. So every single unit in that translation is actually 3 units as if they were before, because we're translating along a scaled vector. And the vector that we're translating along is 3 times as big. Okay, so usually it would go translate first, rotate next, scale finally. That's kind of the way normal transformations would go in a normal kind of computer game, fairly realistic setting. But it's fun to experiment with these and see what happens with all of this. But generally, if we just say this thing is here, it's oriented like this, and it's this big, then we'll do it in that order. We'll first go to the position that it's at, then we'll rotate it for its orientation, then we'll scale. That means each of those transformations has the least effect on the ones that come after. All right, so this one is now bigger. How do I make the purple one smaller? What values would make it smaller?
0.5.
Okay, 0.5 would make it half as small. Okay, so it's smaller there in the background. I want to do one thing with the blue one. I want to kind of flatten it out. So I want to take a scale here, and I want to make it 0.2 in one dimension, but I want to make it 2.5 in one dimension and 1.5 in another. So we're kind of making something like a wall structure here. So we can see the blue one up here. It's kind of flat in one dimension. All right. So rotations as well. Where are the matrices? So what values do we want for the rotations? I would actually say I'd like to have separate rotation functions for each, so I can do them in the order that I want. This is a little bit more complex than the other ones. What I would probably in the end want is to say I want an angle, and then I want 3 values that represent a vector that I'm rotating about. But to begin with, let's stick to the base rotations. We can look at the other one later on. There's no problem for you if you understand these to just kind of Google what the matrix looks like that rotates about a particular angle. You can Google what a quaternion rotation looks like if that's something you need, so on and so forth. But let's start with the base ones. So, rotate x. So there we'd like just an angle. So we're going to need to say something like c equals the cosine of that angle, and I'm going to just have the angle in radians for now. If you want your angles to be in degrees, you have to multiply it by pi and divide it by 180 in order to make sure that you can send your angle in degrees in here, and the cosine will be properly calculated. Angle here, this is about x, so it'll be cosine minus sine. No, sorry. This is 0, this is 0. It'll be here. Cosine minus sine, sine cos. So now I can rotate around x. Let's just add the other ones right away. No, I didn't define s, that is true. S equals the sine of the angle, like so, like so. So this is around y. That'll be cosine sine. This is 0, this is 1, this is 0. Minus sign here, cos, fine. And this one will be about the z vector. It means we have 1 here, 0 here, 0 here, sine here, cosine here, minus sine here. Okay, let's just try one of them. I hope I made them all correct here. Doesn't matter, you'll just fix them if you're following this on the video. Main program here. This one was the one that's kind of flat. Let's rotate it a little bit around the y-axis. So first translate, add add rotate x. It should be add rotation x. That'll be a more sensible name for it. Anyway, let's just rotate it pi divided by 4, which is basically 45 degrees, and see if this works. Was that around the x-axis? Yeah, so it's tilting towards us. I was going to do it around the y-axis, and then you can combine these, do all kinds of things, whatever you like. Oh, I wasn't going to do that. Oh well. Okay, we kind of need this rotation to be a little bit of motion in it. So let's, we have an angle here, and we're changing it, so let's just use self angle here. So instead of this, let's use self angle, and let's see if, with the rotations, it's usually nicer to have something moving just to see how the rotation is working. Okay, so it's rotating in that direction. If we rotate it around z instead, it'll be rotating in a different direction. Seems weird, but I'm thinking it's the way the light and camera is affecting it rather than the rotation itself is weird. I think it's fairly normal. It's way out there in the perspective distortion anyway. Let's see what lab exercise 3 had more for us here. So we've added all of these. Okay, okay, this doesn't really go all the way here. That's the next exercise. So what we'd like to do here at this point is just to see if we can build a bunch of things. And there's actually one thing I'd like to see if we can do something like for y in range I don't know how big we should make this. 10, range 10, inside that for x in range 10, and inside that for z in range 10. So let's make a cube of cubes. For each of these, we are going to, and this is actually an optimization. I'll let this be the last thing I'm going to do in this video. I'll just do a video on the camera part later on, or a separate video. There's one optimization I wanted to look at here, but first let's see what happens if we go in here. Let's skip the rotation. Let's scale each one of them to, okay, so in each of these we are going to, let's say, -5 plus x, right? That makes sense. So I'm going -5 and then I go up one, so it'll go from -5 to 5, more or less. I want to go here from -5 plus y, since y is going from 0 to 10, plus z. I'm going to transform each of them, make them a little bit smaller, so there should be a little gap between them. Actually, z, I'm just going to start at, Yeah, I'm scaling them to 0.8, so I'm making them a little bit smaller than 1. If they were all 1, they'd be like flush next to each other, so it would be like a giant cube. Instead, this should be like cubes that have a little bit of a space between them. Set this matrix, draw a cube, and let's just skip the other cubes. So, comment this out. We'll keep the yellow color in here. So this should all be yellow. Let's just see if this at least compiles and see if it gets super slow. Okay, whoa, that is not what I thought this would look like. And since I don't have any control of the camera, it's really difficult to... let's rotate them anyway. Wait, where's the display function? Here, let's add a rotation by angle around something like the z-axis and just do it before. If I do it before, it'll affect everything else. So we'll just push matrix at the beginning and pop matrix at the very end. So that means this rotation will affect all of them. You can see, of course it's clipping, that's why it looks so weird.
I got a really massive shot by...
I just need to move it a little bit further. Okay, this is super slow. And I'm going to see, it's going to be slow on my computer with the recording going on and the projector. But I'm going to make it a little bit less slow, I hope, with a very valuable tidbit of information here. But first, I'm going to take it a little bit further away. Say I'm going to start at, no. This should be, yeah, this should be starting at -5 and do -z. Let's say starting at 0. Then it'll move away from us because the z, we're kind of looking along the negative z-axis. Okay, so there we have this huge cube. And the motion here is just so we can see the frame rate. This is the frame rate. And what are we drawing? 10 by 10 by 10. We're drawing 1,000 cubes. That's nothing. It shouldn't be this slow. So this is ridiculous frame rate.
I think I know what it is. You have push and pop in the back.
Yeah, I have push and pop in here, but that's not the biggest problem here. What I want to look at here is in the base 3D objects. So what's happening is that for every single cube that I draw, I am also sending values for the vertices into the shader. So I'm basically copying values from my main program into the graphics accelerator, my graphics hardware, every single time I draw a cube. If I were to change this and instead say, okay, define set vertices, self shader, I'm going to make a specific function here just to do this. And that means that when I'm using this, I can say if I'm going to draw a lot of cubes at the same time, I can just do this once. And then these are the vertex lists that OpenGL will use. Then I'll just draw all these cubes. So drawing the cubes is fast. But actually sending values from my main CPU, basically, into my GPU is taking time here. So once I send this down, everything is happening in my graphics hardware. I'm just telling my graphics hardware, read this, do this. I'm sending tiny information, and then it does all the work down there. When I'm doing this, I'm actually sending data from one part of my computer down to another, which is not what I want to do. I want to use my graphics hardware in a way that I can send as much stuff as I want, as I can down there, and then just tell it what to do with it. So it's working in its own memory, not sending things between my main memory and my graphics memory. So I'm going to see if this fixes the frame rate. I'm not sure it's going to be a good frame rate, but I'm hoping that it'll be better than what we saw earlier. That, however, means that before I start drawing these cubes, I need to call this function. So I'm going to say cube, self cube, that would be. set vertices, self.shader. And actually, if we go in here, we don't even need to send the shader in here. We could throw this out. But for now, let's not worry about it. Let's see, number one, if this works now, and if it's at all faster than what we had before. Well, it's faster, but it's not fast. On my computer, though, at home, this kind of is super smooth at this point.
It's getting faster.
It is getting faster. Anyway, I have the recording software. I'm sending things over the internet. I'm doing all kinds of things on this computer at the same time. Unless there are any questions or anything in particular you want to see, I'm going to end this video now so I don't kind of bloat this video. I'll take the camera part of this either later today or soon, after you've kind of gotten a chance to work on it a little bit yourselves. But for now, I'm gonna say we've kind of gone through our lab assignment 3, our first three-dimensional lab assignment. We've gotten objects to appear. We have 3D objects. We can scale them. We can move them around. We can rotate them. We can draw them in different colors. So that's something. We can start building structures from this. But after we've got some structures going, it's nice to start moving the camera around and getting control over that.